Hi, everybody. I'm Dean Mertz, K0MKT, and I've been a ham since just out of high school, so call it 40 years or so. Electronics experimenter even before that, and of course, always been interested in test equipment. In fact, the very first piece of test equipment that I built was this, which some of you might recognize. A little Heathkit transistor checker. I built this when I was 10 years old and still have it. It's in the bottom of a box in the basement, which I found looking for things for the presentation. So anyway, I just retired from Raytheon Company, about 32 years as a radar systems engineer with Raytheon. With a little break for about 3 years in the middle of that, I worked for Hewlett-Packard and Agilent Test and Measurement in Colorado Springs on oscilloscopes and logic analyzers, things like that. So I've had a long history with test equipment, always been very interested in it, interested in electronics. So this is a big topic. There are lots and lots of pieces of test equipment, lots of models, have been around for a long time, and people have been using it. Hams have been making their own test equipment for years. Everybody has opinions, I'm sure. Some of you are new to the hobby and may not have used some things, so we'll try to give you an idea of some basic equipment that you might want to see in your ham shack. Those of you who've been around for a long time or in the industry, I'm sure you'll have opinions and suggestions and ideas, and we want to hear those. We really would like to, we'd like to get some feedback. So if anybody has questions because they don't understand something or they want more information, if you have opinions about test equipment, ideas, things like that, suggestions, please either put a comment, type a comment in the chat, or turn your microphone on, and we'll address that. So we'd like to get, we'd like to get lots of comments and questions if we can. Very good. So I've done a lot of traveling through my career as an engineer. I spent a lot of time in Asia, especially in Taiwan. And I always like to go hang out at the, the various electronic districts. So in Taipei, that's the Guang-Hua Electronic Plaza. This kind of little modest entrance leads to a huge 3-floor underground warren of dozens, maybe more than that shop, maybe 100, over 100 shops. Some little tiny shops selling cables, parts, test equipment, things like that. And they always have really interesting things. So of course, being a ham for a long time, I've seen some pretty interesting little pieces. These days, we're seeing some small, interesting pieces of test equipment, and very cheap. And I wondered, is this stuff any good? Does it really do anything? Does it work? Is it like the fancy, expensive stuff that we use, at the radar sites? So we'll take a look at some of those today too. Okay. So first, we'll talk about basic test equipment for the ham shack. So these are just some items that I found useful. Some of you may have other things that you'll suggest too. So we'll bring those up and we'll talk about those too. Okay. So everybody needs a meter, a multimeter. Prices range all over the place. Pretty typical Fluke 115, a pretty typical if it's true RMS AC voltage. The cheaper ones, average. So, if you need that, you have to decide if you need that feature. So basic experimenters probably won't. Auto ranging is, I would say, it's a must. Otherwise, you have to decide what voltage you're measuring and set the range. So that's a great feature to have. And this Fluke It's one-handed operation, which is pretty cool. You can use your thumb to turn that. That's very handy, especially working in, most of the time I'm working in a radar equipment shelter. It's a 20-foot long by 8-foot by 8-foot shelter packed with equipment. So that kind of feels what it feels like here today. We have lots of equipment on the floor and on the little bit of table space that we have here too. So kind of bear with us as we move equipment into the field of view and test it. Okay, so let's see. Little fancier meter, the Fluke 179. I've had one of these for years. Actually, I've had several of these and worn them out, given them away, or had to recycle them just throughout the years because they get a lot of use. They get dropped. The Flukes are great though. They take a lot of abuse, but they're also quite expensive. The 115, you can see $150. Not too bad, but you know, if you're just getting started, or you know, if you're on a budget, then you might want to consider some of the later examples here. The 179, 325. And you can sometimes find these on Amazon Black Friday specials too. I was looking on Black Friday and found a couple of interesting specials. So there are tons and tons of budget meters on the market now. And just looking at specs for the meters and cost, I think this X-Tech seems like a pretty good deal for a basic experimenter, basic hobbyist. It's not true RMS. That's really maybe a feature that you don't need, you know, as an experimenter. But it is auto ranging, which is quite important. They make a big deal of it. It has an AC voltage detector, so you can tell whether your outlets are powered up. That's kind of a nice thing. This one also has capacitance and frequency meter, like an LCR meter, but no inductance measurement. Thermometer comes with a thermocouple. That's quite useful. I've used that when we have airflow problems in equipment. You can stick the thermocouple in and close the cabinet door carefully around it, or find a way to snake the thermocouple in and measure excuse me, temperature. Or if you have a chip that's running hot, or heat sink, those kinds of things too, I'll put them inside the equipment and monitor the temperatures. So $50 new on Amazon. That's a pretty good meter for the price. Now, if you're really on a budget, then you can find meters for $12, and even cheaper too, digital meters. Yeah, well, not true RMS, not auto ranging. It does have a transistor and a diode tester in it though. So I don't know, most of us don't really work with discrete components like that quite so much anymore. I don't know, some of you may, but anybody have a favorite meter that they wanna bring up?
260.
Oh, Simpson 260, yes. Well, I have one of those in the basement, and I almost brought it, but I was already bringing an armload of stuff, and I knew we'd be kind of pressed for space. That's an analog meter. That's kind of the classic volt-ohm milliamp meter.
Good for high voltage.
Yes, well, yeah,
That's what I use it for.
right. Analog meters are very useful, nice to see trends. Digital meter, if you're trying to watch a voltage change, or you're trying to tune something, then the digital meter is going to hop around. Really hard to tune if you're looking at, you know, voltage for tuning. Analog meter is quite nice for that. And you can still find cheap analog meters, eBay, those kinds of things. I don't know how many of those I've had too. I think the first one I had was probably back in the mid-60s from Radio Shack. So
Klein makes a pretty inexpensive VOM auto ranging. You can buy it at Home Depot for about $60. Really nice meter, surprising.
oh, okay.
Simpsons are not cheap.
No, they're not. No, those are. So what we find in test equipment is that there are a lot of old names in test equipment. Hewlett-Packard has been kind of the preeminent brand. Fluke for certain kinds of HP for RF and basic instruments, Fluke for handheld meters and now also handheld scopes. German manufacturers like Roth and Schwarz, Wandel and Goltermann, very, very nice stuff, very, very expensive. I'm talking a benchtop meter, just a multimeter, you're talking, you know, $10,000 to $12,000. And it's remotely programmable. It's something that you would build into an automated test rack. But as hams, we typically don't need to do that because we're making one of something as a, you know, experimenting with something. We're making a one circuit, not doing production. So,
Hi, hello.
yeah, hi.
This is Glenn, WB0DKT. Would you go back for a moment, please, to the Fluke picture? There is a feature on those that there. So one of the things that I find very valuable is the fast ranging bar chart on the bottom. When you're looking for intermittent or something that is jumping around, the digital meters are slow sampling, often just once per second for the digital. So there's no way that you can find something that's intermittent or in the case of a pulsed transmission, see how much the voltage is dropping during a short current load, maybe when the transmission pulses. But it's very valuable to have that bar chart that's on the bottom of the Flukes, because although that you can't get an exact value on that, that's very fast sampling. And so, you know, where we used to look at the twitchiness of the needle on a Simpson 260 or an old analog one, the bottom bar chart is great for like peaking something if you're adjusting something and trying to get to the peak or the dip, and also for looking for, you know, intermittence. You're wiggling the cable and trying to see if you know, the resistance jumps around or something.
Yeah, exactly. Great point. That's a really nice feature, and I do use that all the time. It kind of harks back to the analog days and their applications when, as you said, you really, an analog meter is a better solution. But so they've implemented that concept very nicely here. So great point. Any other question?
Yeah, we have a question in chat from Dave, WA1JHK. I think when you were talking about, you know, Amazon and some things, and the question is, how about a Harbor Freight VOM?
I actually, I've only been to Harbor Freight a couple of times, so yeah, I don't know. Do you have one? You want to render an opinion?
Sometimes they're free if you watch the coupons on the Harbor Freight website. You can actually get a free one. For those of us that repair repeaters on mountaintops, if you grab one of the free ones and you leave it at the radio site so that you always have a voltmeter when you're up there. So it's good for checking power supplies and, you know, the simple stuff that you might come across. And especially if you're just getting started and with amateur radio or electronics, it's great to have just a meter, even though it's nowhere near the quality of the others that you've been showing. It's better than a light bulb.
Yeah, that's true. Unless the meter becomes a fuse, and that's happened to me a couple times too. Yeah.
They're actually very close compared to accurate meters I have. Been very surprised. It's worth having a few around.
Oh, great. Yeah, great point.
As an example, here's one that I'm just holding up to the camera. Well, I guess I should turn on the video if I want to do that. This is like a $30 meter from Harbor Freight. It's not auto ranging, but it will measure frequency and capacitance and everything else that, you know, one of the more expensive meters measure. I can't attest to its precision necessarily, but, you know, it at least has all of those features.
Yeah, you don't always need precision, and we'll talk about that in a minute too. The difference between precision and accuracy, That's an important thing. And then we've talked about the handheld meters, but there are times when you need a little bit more resolution. You can find a bench digital multimeter DMM, and these can be quite expensive, as I mentioned before, tens of thousands of dollars. Or here's a used one. I've seen these for about $75, a Fluke, and it'll read a milliohm, which is kind of nice.
Hey, Dean, we have another question from the chat. James wants to know, what is the meaning of RMS? Everybody may not be hip to all of the lingo.
Okay. Well, we have such a diverse group here. We have people starting out in the hobby, new, as I mentioned, and we have people who are seasoned engineers, and we have people like me who were engineers for a long time and then have spent too much time in management lately. So trying to get back to my roots now that I've retired. Yeah, so when you measure a DC voltage, a direct current voltage, the voltage is the voltage. It's not, there's no AC waveform. So alternating current, of course, the current flows one direction, and then once it reaches the top or the bottom of the cycle, then it flows back the other direction. And so you have a sine wave, but RMS is a way to accurately measure that voltage, and it's essentially what the equivalent voltage, DC voltage, would be to, like, if you have a resistive load like a heater or something like that. If a certain DC voltage would heat that to a certain point, an AC voltage, because it's not constant, you would need a higher RMS voltage to heat that the same amount. So it's a way to repeatedly measure an AC voltage. Let's see if this works here. Oh, okay, there we go. Yeah. So oops, sorry about that. Yeah. So we essentially are measuring the voltage under that curve, and we have to do a mathematical operation on it to do that.
It's actually doing calculations in real time.
Yeah, exactly. So a non-RMS meter will take an average in there. And I'm not actually sure how they do that, if they integrate that with a capacitor or something like that. Dave M, do you know that?
I don't.
Okay, yeah, I'm not sure. I've taken one apart because I've used RMS meters for probably 3 decades. But yes, they actually have to do some math in the meter in order to calculate that voltage.
And our math professor, RMS, he puts on chat root mean square.
Root mean squared.
So we've got to have some math in here.
Yeah. Okay. So we'll talk a little bit about accuracy and precision. When you buy a meter, the company that makes the meter might say it's high accuracy. It has 1% accuracy or 0.1% or something like that. What does that mean? What is precision? And then how many digits is the meter, for example? So if something is accurate, the measurement it's repeatable, and this actually is the goal right here. So this is these measurements are very repeatable, and they're not very precise though. So they're within some range of what we want to see. So this is an accurate device. but it's not very precise. The measurements that it's taking all kind of gather around where we want to be, and they're all very repeatable. Precision, the measurements that we make are all very close to one another. They don't vary, but they're still not on target. So what we really want to see is, we want to see that cluster of measurements close to the target, all very close. So we can, because of the laws of physics, we can't make a perfect measurement. There's always some uncertainty in the measurement, but we can do things when we design the test equipment to make it more accurate. We can correct for things like temperature variation, which affects the components, causes the measurements to vary and change. And precision, we can add more bits, for example, to the analog to digital converter to get a little more precision. We combine those together, then we can design a piece of equipment that is both accurate and precise. And then, of course, this might be your Harbor Freight special here. But it's still within a green circle, and it gets the job done. You don't always need to get exactly right there. Sometimes within green circle is good enough, for a go no go kind of check, something like that.
It's better than putting your tongue on it.
Say again?
It's better than putting your tongue on it.
Yeah, that's right. Yeah, 9-volt battery. All right. Okay. One kind of nice feature that a lot of the meters have, even the cheaper ones, is the diode test. This is kind of useful, and I get asked about this. I find quite a few people aren't really quite sure how to use that little diode. There's a little diode symbol right there. So essentially, when you put the meter in diode test, it applies a bias to the diode so that the junction in the diode is biased, and then it actually measures the voltage drop across the diode. So you can see if it's good. Silicon diode will have, typically 0.6 volts, give or take a little bit. A germanium diode, about 1/4 of a volt. And of course, if you reverse bias it, the diode will not be conducting, and it should be 0. Beg your pardon?
Hopefully.
Yeah, hopefully, if it's doing its job, that's right. If the diode's open, it should be 0 in both directions. And if it's shorted, could be 0 volts, could be a dead short, or there could be a little bit higher impedance short in that too. So it's just a really nice little feature. And I have been asked about that. I get asked about that pretty regularly every few years. This is something that we teach when we teach maintenance courses for radar systems. Most of my customers have been overseas customers. So it's really interesting trying to explain the concept, the diode test, when it's going through a translator, into Mandarin or something like that. So that always makes it interesting. I've done a similar presentation to this one, basic test measurement, those kinds of things for my customers. And typically, what we're doing here in 2 or 3 hours would take 2 or 3 days, because each slide has to be, I'll speak for a few seconds, and then it has to get translated into Mandarin, and then usually in Taiwan into Taiwanese too, which is a separate dialect. So that makes it interesting. So, and I don't get a lot of questions.
Yeah, there was just a couple comments.
Yeah.
I know Mike K7AIH pointed out on chat that a precision instrument can be calibrated to be accurate. And then Richard Bush, WB0 EVA, pointed out that an ohm meter on low ohms can be used to test diodes as well.
Yeah, it can, because they do have to put a bias on it. I think the diode test position just puts probably more of a bias on the diode, or more predictable. But yeah, you can certainly check continuity of a diode. One
of the most useful features of the diode test is that on most meters, there's actually a little beeper connected to it. So if you can't actually look at the screen, it's very convenient to be able to use that feature to just check continuity of a piece of
Yes,
equipment.
exactly. Yeah, continuity checker, the beeper ringing out a cable, for example, we call it, or some people say beeping it out, of course. But yep, super useful feature. And I haven't seen that on the really, really cheap meters before. I imagine this X-Tech might. It has a diode checker. That's got a beeper too. Good. Yep. Right there. You can see the beeper. There. Good. Okay. So again, this is a really basic piece of equipment, and we'll talk about much more complex pieces of equipment too. But you use this so much, just day to day, or if you're working on a project, as everybody has mentioned. Okay. Probably the most useful basic piece of test equipment is an oscilloscope. And I get asked lots of questions about, which oscilloscope should I get? What do I need? What's good? What do they cost? Or I just saw a Tektronix 465 here at the Swap Fest. Should I buy it? And we'll talk a little bit about that too. Oscilloscope, there are generally a lot of opinions about this too. So of course, please, chime in if you have comments. So, yep, the Tektronix 465 introduced in 1972. This was the first scope that I used when I was a student engineer at Ford Aerospace Company in Southern California back in the late 70s. This was kind of the workhorse. It's a great scope, 100 megahertz scope. That's the 100 megahertz bandwidth on the vertical amplifier. So the input channels are here, channel 1, channel 2 down there. That, let's see. Oh yeah, here we are. Okay, so 2-channel scope. Probably the most desirable feature of this scope was, of course, all scopes had cathode ray tube displays in them. This one had a 18.5 kilovolt accelerating potential for the CRT, which meant that you could see really, really short signals. You could see like a nanosecond glitch or something on the edge of a pulse, just because with the high accelerating potential, it would actually, the beam swept across so fast that if you had a nanosecond pulse, they're in a scope with less voltage on the CRT, just wouldn't show that trace. And so this one did very nice. This was a light and portable scope for the day. It still was 25 pounds or so. And I've lugged these on planes before many, many times, carry on, that kind of thing. And they're $150 to $250 on eBay still. There are lots of them around.
We'll sell them at the Ham Fest for between 150 and 200 most of the time.
Yeah, they're still solid. People know them too. I mean, if you've been around in the industry for any length of time, people know them and they're really comfortable with them. You can do lots of measurements. You can do offsets, and it'll zoom in. You can set up a waveform, and then you can zoom in on like a leading edge or trailing edge of a pulse. It's quite nice. But parts are kind of expensive, and it always seems to be the same things. I mean, if the knobs tend to break off, so trying to find one of these custom coaxial knobs really tough. So I found quite a, especially this one, the time base, the horizontal sweep, this knob with a couple of coaxial knob functions in there too. These things break. The button caps pop off, those kinds of things. And of course the CRT is, those tend to wear out too. So I've seen quite a few of these where they're burned. Yeah, you have to be careful not to leave them on, take care of them. So yeah, but they do give a nice clear picture. You cannot they make a storage version of this. Tektronix makes a similar digital storage scope where you can actually capture a waveform and store it. The problem is there's no way to print it. There's no way to put it in your notebook or presentation. So we always had a Polaroid scope camera, which was which fit over the screen with black and white Polaroid film, and you take a picture of the waveform and pull the film out, and a print would develop, and then you could put that in your notebook or put it in a presentation or something like that. So we've come a long way since then. Most of these other scopes I have.
Hey, Dean, on
Yes.
the chat, we've got Paul, K0, WSU. Are you going to show us how to connect this to a circuit and make a measurement on the scope at some point?
Yes, we do have a couple of scopes here, and we'll do that in a minute. Let's talk about our survey. Yeah, here, in fact, so this is a kind of a medium price scope. This is what I have. We have one over here. Yeah. Okay. So yeah, this is a 200 megahertz scope. It's 4 channels. Now, digital scopes actually have to sample. So this is like the difference between analog audio when you had a record or you had tape, and we moved to digital audio with CDs where there's a sample rate involved where we're actually making a approximation of the analog waveform and digitizing it. So yeah, these things they're about $4,000 new. I bought this a few years ago. It was a little bit less, but it has tons of features. It also has tons of options, and that's kind of what we're seeing in the test equipment industry, the marketplace nowadays. Companies will make an oscilloscope like this, and they build features into it that are kind of hidden, and then you have to pay extra for license keys, which you'll enter in the front panel to enable them. So like, for example, this scope has a function generator for generating sine waves, square waves, pulses, white noise, those kinds of things. It's very useful. It's nice to have it with you so you don't have to carry a second piece of test equipment, but it's a $500 option. So this can get expensive pretty quickly. There are lots of deals though. If you watch the manufacturer has promotions, and so yeah, I paid about $3,000 for this scope, and there was a deal probably about 4 years or so ago where I got a bunch of the options for a couple $100. So it turned a bunch of the digital diagnostic options. It turned the wave generator. So yeah, watch for the deals on those. I haven't seen too many of these used, but so anyway, yeah, let's put a signal up just for fun. So the scopes nowadays, it's not CRT. This is a LCD screen. I mean, it's really basically a computer nowadays. All right, let me turn on the wave generator. There we go. We have a sine wave, a 700 hertz sine wave. So when I turned on the waveform generator, that's this option here, the menus at the bottom changed to let me control the waveform generator. So I have waveform type, if you can see that, sine wave, square wave, ramp, pulse, DC, and noise. Let's just go back to the sine wave for a second here. All right, this is a sine wave, but the scope it's not synchronized with the sine wave, so we're seeing as the sweep is repeating, we're seeing that sine wave drawn kind of asynchronously over and over again, so it fills that space up. So we need to find some way to synchronize that so we can get get a nice clean view. And one feature that you find on scopes now, and I've had some people argue that this is a must-have feature, and some older school colleagues of mine say that this is cheating and you really should know what you're doing. You should know what you're looking at and be able to set the scope up for that. There's an auto button. Watch, you push the auto button, the scope will look at the waveform and it'll lock in on it and give us a nice sine wave. We also have a measurement of frequency. The scope is doing all this for us too. It's 700 Hertz. That corresponds with the frequency that we've dialed into the wave generator. 1.42 millisecond period for the waveform. So it's doing the math for us there. And we can look at the markings on the scope, the graticule here, and we can see what the peak-to-peak voltage is, or again, the scope is telling us it's 1.65 volts right here.
So how do you count that on the screen?
All right. So
Can you repeat the question?
Yeah,
We're-
John's
John.
asking-
we're
John.
gonna talk about actually reading the markings on the screen here.
This goes for any device.
Let's see. There we go. All right. Okay. All right. So first, let's just kind of go through what we would need to do to make a measurement. First, we pick a channel. We've got 4 channels on this scope.
Speaking of 4 channels, Willem was wanting to know, why do you need 4 channels?
You want to look at more things happening simultaneously. For example, in the radar system transmitter, there's kind of a sequence of operations that have to happen. There's a RF exciter that generates the transmit waveform, a pulse waveform. There is it generates that at about plus 10 dBm, about 10 milliwatts. Then there's a intermediate amplifier that amplifies that up to about 500 watts. And then that drives a klystron tube transmitter, and then we get up to about 1.5 million watts peak power. So the klystron has to be pulsed. And we have to guarantee that the RF is applied to the input of the klystron a few microseconds before we apply the 80,000 volt 3 amp pulse to the tube to generate the transmit waveform. And having a 4-channel scope would let us take a look at the trigger, the exciter being triggered, and we could look at the switching in the intermediate amplifier to make sure that it's happening at the right time. And then we could also look at the waveform, the high voltage waveform, and then we might actually put a current probe on that 80 kilovolt input and take a look at a current waveform, line all those traces up, and we could see that we had the required 1.5 microseconds from the first operation to the next, to the third, to the fourth. And that's why we might use 4. So that's just one example. But of course, you have your own.
There's another question in the chat from Paul, K0WSU. He says, please show us how the probes are connected as well.
Okay.
And then I also, I guess from my standpoint, maybe talk a little about a 1-to-1 and a 10-to-1 probe. We typically see that, or unless that's something you've got later on.
Yeah, actually, no, that we'll do that here in a second. But we were going to talk about. Can you see the markings on here? So there are 1, 2, 3, 4, 5, 6, 7. There are 8 markings this way. 1, 2, 3, 4, 5. So there are 10 this way. And let's see. Where's my, all right. I don't know if you can see up here, but this is the time base. This is how fast, or what the amount of time is that it takes for the scope to draw this trace out. So we set that using the horizontal control. And right here we see that each division is 500 microseconds. So if we move the peak of the wave to the center, there's 500, 1,000, and about 0.6 or so, 0.7, something like that. So there's our 1.65 milliseconds, or 1,670 microseconds. If we turn that down at 200 microseconds per division, now you can see the waveform is spread out a little bit because the amount of time is less per division. And then the voltage right here, this is now set at 1 volt per division. So we're looking at about a little less than 2 volts from the peak to the peak there. Now the scope actually takes a look at it's looking at all these samples, and it's computing, finding the low point and the high point, puts these markers up here. And it's telling us that peak-to-peak voltage is 1.6.
So what would the RMS voltage be?
Someone said, what would the RMS voltage be?
Oh, you want me to calculate that, or are we gonna? Yeah, it should. It's hard to do that from back here. Let's see. Measurements. Add a measurement.
Some of the new digital scopes do a much better job of doing calculations than the older ones. The older ones, you actually had to read the graticule on the screen. The new ones will pretty much do it for you.
Yeah, exactly. I know it can do it because I've done it before. I spend most of my time looking at pulses, so I haven't been too interested in that. So that's my excuse. Sorry about that. It can do it. The thing is, like everything nowadays, there's an app for that. There's a menu entry for that, and it's infinitely configurable down here too. Let me see if I can find that. More measurements. Add a measurement. AC RMS, 545.7 millivolts. All right, so let's take a look at probes too. That's another important topic. All right, so the input to the scope it's typically always a BNC connector. That's very, very common, BNC connector. And so I was just using a BNC cable, direct through 50 ohm cable, to take the signal from this is just it's actually a separate instrument function generator that's built in there for convenience. But when you're working on a circuit board or you're working in a piece of equipment, you'll use a scope probe. So the probe has got a needle point. It has a ground connection. The ground's very important. If you don't connect the ground, then there's no reference, and so you'll see noise. You might see some signal, but
So what's the thing in your left hand?
this is a hook tip. The hook tip fits in like that. And when you push it, it gives you a little hooky that you can hook on the lead of an IC. You can hook it on a transistor lead or a resistor somewhere in there. These are pretty basic probes. You can get very, very small. I have some hook tips that we use with logic analyzers that can actually fit on IC leads that are 0.5 millimeter spacing on a surface mount.
This one shows it's a 10-to-1 passive probe, 300 megahertz, 10 megohms, 15 picofarads that it's going to add to the device that you're testing.
Okay, so 300 megahertz, that's useful to know. We need to know that it has the bandwidth to handle whatever the rise time of, say, a pulse. This is going to be really important because if the bandwidth is not high enough, then it's going to affect the pulse. It's going to round it off, and we won't get an accurate measurement on that.
So
question?
This device, when you connect it here to the scope, essentially turns this into almost a voltmeter, correct?
Yeah, well, an oscilloscope really is a voltmeter. It's a graphic voltmeter, graphical voltmeter that displays voltage over time. All right, so typically these probes, there's a voltage divider inside, and so they'll talk about a probe being 10-to-1, which means that 10 volts on the input actually shows up as 1 volt here at the output. That's corrected for in the scope. This scope, let's see. And when we plug the probe in, we'll have to go to the probe menu and make sure that, oh, okay, the BNC cable has no voltage divider in it. So it's 1-to-1, 1 volt in, 1 volt out. This 1 volt in, 1/10 of a volt out. So in order to measure accurately, we need to make sure that the scope knows that this is a 10-to-1 probe. So now it's 10-to-1. And we can check this. All scopes come with a, nowadays anyway, come with a calibrator. It's a, put that there.
They
So
come with a calibrator for many years also.
Yeah, exactly. Uh-huh. Let's see, we're on. 1, 10-to-1. Turn that off. Where's my? Have that on. Oh. That seemed loose. This happens too once in a while. Sometimes the probe tip is not seated. Very often that little guy is broken off or bent. That happens a lot. These are kind of delicate, and these are almost a consumable item, at least on a radar site. And of course, this worked just fine last night. Typically, the scopes come with fairly cheap probes too. Some of these probes, they can get very fancy and get very expensive, hundreds of dollars. I wonder if this one's bad. Let me grab another probe. I will be right back. There we go.
Is the bar in the center the ground, or is the bar in the center the signal?
Well, it's the current signal, which is 0 volts. So that's the 0 volt reference. So the scope is continuing to sweep, but there's no input. So it's we're looking at 0 volts. Let's see if this does a little better job. Yeah, you know what? There we go. Okay, that's the problem.
Operator error.
Operator error, because standing up here, I can't read that the ground is in the middle. All right. All right, so what do we got here? We're on 200 microseconds per division, 4.5, so about 500 microseconds. So that's about 1 kilohertz. Another thing with these probes that you need to think about, to preserve the high frequency response, so the 300 megahertz bandwidth, they use coax, and they're compensating capacitors in here, trimmer caps, to compensate for the inductance of the lead. So if you take a look, let's see here. Not much of an adjustment there. Yeah, I have a probe that's a little better for that. Demoing that. Let's change probes here. So this is actually a fairly cheap probe. It came with the scope I just bought for a demo.
From the Guang-Hua Plaza.
Amazon Prime.
Oh.
Black Friday special. And on.
Oh, no.
All right. Where's the compensator? Huh. Okay. So yeah, that one's pretty compensated, but let me just show you this here. Trimmer caps in there just to ensure at this frequency, we really at 1 kilohertz, they're not much of an issue. So we didn't see much of an effect, but at higher frequencies, you'll put a reference in and then you'll adjust these trimmer caps to get a nice square waveform. And this will compensate make sure that the edges are nice and square. Okay, let's look at, I've got another source here too that'd be interesting to look at. We'll talk about this a little bit later too, but this, and I'm kind of stuck to the, yeah, got some cables here. This is a GPS disciplined oscillator. So it uses the global positioning system satellite system. So here's the antenna. The patch antenna is sitting over there on the ledge by the window over there. There it is. And this has it's a programmable oscillator. Typically you run them at 10 megahertz. This one's set for 10 megahertz. So, and it's not blinking, so it's synchronized with the satellite. So here we have a 10 megahertz output. Let's take a look at that on the scope, just for fun. Okay, well, first thing we can tell is that that it's a digital output. It's not a sine wave. It is a square wave.
Got a little artifact to it.
A little bit of artifact, yeah. So I bought this because I'm going to use it with a IC 9700 for microwave work and for EME, moon bounce. A good friend of mine has been trying to get me into moon bounce for some time, and I'm about ready to take that plunge.
Moon bounce from Highlands Ranch.
Yeah, Highlands Ranch to, you know, Switzerland or Washington State or wherever it needs to be. But
You put up a 30-meter dish in your backyard.
I'm starting with the 7-foot dish, but yeah, it's coming any day now. So we'll get that set up. But the company that makes this little oscillator, and there are lots of these. We'll talk about this too. There are a bunch of these. This happens to be a nice small little one. This is a Leo Bodnar Electronics in the UK. Sells this. It's about 200 pounds, so about $250, $260. And he actually sells an injection board that fits into the IC 9700. And you connect a cable, SMA cable here, and inject in a nice stable 10 megahertz signal, because moon bounce needs a very stable oscillator. So let's just we'll take a quick look at this. Let's see. So this I should be able to use this to calibrate my scope. So let's see if it's ready. Okay. And then we'll take a break. So let's see. It's telling me the frequency is 10.00 megahertz, period 100.0 nanoseconds. That's exactly what we expect. So my scope is still decently calibrated, and we'll talk about that a little bit later too. So do we want to take a 10-minute break here?
9:40, so 10 minutes. It'll be 10 minutes till 10. We'll be back and go get some coffee and get rid of the other coffee. See you in 10 minutes. Okay, welcome back. We'll be ready for part 2. Go ahead, Dean.
Yeah, we've had some good questions come in during the break. One question was about the input to the scope. Oh, and I've changed scopes just so you don't wonder where the other one's over here, it being a signal source, but we'll talk about this scope in a second. Yeah, Dave was pointing out that these inputs to these scopes are fairly limited. You can't put a really high voltage, a lot of power into they're not made for that. So you really do need to know what your scope can tolerate, what the maximum voltage it can tolerate is, because otherwise you will destroy that amplifier, the front end of the vertical amplifier on whichever channel you've connected to, and if it's enough power, it'll fry everything in there. But that is very important to know what the max voltage limit is that you're looking at. So that's one of the reasons why the probes are like a 10-to-1 probe, for example. The input range might be 20 volts. That might be the maximum. But with a 10-to-1 probe, we can look at 200 volts, because 200 volts divided down gives 20 volts at the output. If you're looking at high voltage, like we do in the radar transmitter, you might have 1,000-to-1 or more divider probe. So a high voltage probe will be huge, typically, to make sure that your hands stay away from it. If you're measuring 40 or 50 kilovolts, like we do in the radar transmitter, it'll have a great big handle on it. It'll have the insulator, ceramic insulator, to ensure you don't have arc over, and then you have the probe tip, and it might be 1,000-to-1. And that also has to be calibrated too, because if you're trying to measure a voltage accurately, you're doing a sell-off test or something like that, part of the test is ensure that the cathode pulse is 82 kilovolts, plus or minus 10%. Then you want to make sure that the probe is also calibrated. So that was a great question. Okay.
Question from Paul, K0, WSU. Are those scope devices that use an iPad as an output a reasonable investment?
Yeah, I want to talk a little bit about that too. So personally, I do use PC hosted instruments. Those have been available for a few years now. A small box which has the the front end electronics in it, and they use a PC or an iPad or something like that as the user interface. Those are pretty handy, and they're cheaper. They can make the scope cheaper. I have a logic analyzer I use like that. Personally, I like the instrument to be all in one. I like it to be all one unit with its own interface. So I don't have to worry about carrying a computer, finding a place to set it in, like a shelter somewhere, or if you're on a mountaintop, you don't always have a table. It's on the floor. And then, then you need a tough book like John carries, unless you want your computer. Laptops are pretty fragile. Those scopes work really well, and they range in price from a few $100s for a decent one to thousands of dollars for something like a picoscope that has a lot of accuracy and a lot of features, measurement features. They do tend to put a lot of features in the software. There are all kinds of, well, we looked at the screen here, and you can see features doing calculations, math, and differences between waveforms, and some of them, like actually even this little guy, they'll do fast Fourier transform. So you can put a signal in, and it actually will do a kind of a spectrum analyzer, limited but simple. But the PC hosted instruments do that too. So just my philosophy, I don't care for PC hosted instruments, just because I don't like to have to carry the laptop, and I'm worried about damaging it. So that's just my philosophy. Anyway, other questions? Okay. So another application for scope is actually, I use it for teaching. One of my colleagues from Raytheon and I teach classes in the middle schools and elementary schools, and a scope is a good tool for visualizing. And I've been carrying my big fancy Agilent scope or Keysight scope now, but I'm always kind of worried that when the kids get in there, we have these 5th grader, 4th graders sometimes, they learn to be gentle with it very quickly. But even though we mention it, somebody will always get on there and just spin a knob or something, and it kind of it makes you a little nervous. So I was I kind of did a survey of friends and the market, and wanted to find a scope that would be good for teaching, also be good for ham use, fairly simple but capable, and not too expensive. So you can see from the, do we have the presentation up? Yeah. So Siglent is a Chinese company that makes lots of different kinds of instruments: scopes, spectrum analyzers, power supplies, signal generators, etc. And this little 2-channel, 200 megahertz scope was $379 at Amazon. And actually I got 15% off on Black Friday. So I ordered it, and it just showed up a couple of days ago. I haven't had a chance to play with it too much, but it does a lot for $379. Siglent makes cheaper scopes too. They make a $259 scope that was 15% off for Black Friday. So a couple $100, that's actually a pretty good deal for a scope. I haven't really put it through its paces yet to see exactly how accurate it is, but it seems to do just fine. I'm using my big scope, just the little audio generator here, the waveform generator, to put a waveform in, and you can see we have the display. It's nice and stable. It's clear. It's got a little USB connector on the front. You can capture the screen, the waveform, when you have it set up. There's date and time on there as well, and it saves it as a PNG file or a JPEG, and you can choose the format. And you can put that in presentations, or you could put it in, you know, an email or something like that if you needed to send it. Again, it's menu driven on the bottom there. Just a subset of the controls on this bigger one, but it also has, I mean, at $379, it has the auto setup, which is a great feature. And somebody asked me to go through setting the scope manually. So this is what you should know, but all engineers should know, and technicians anyway. We if we're looking at that would have been, okay. And again, the writing is real small on here, but yeah, well, it's just hard off axis here. So yeah, 500 microseconds. So it's 1 millisecond, two divisions is about a millisecond, right? So there's our 1 kilohertz, or I'm sorry, it's 700 hertz here. Let me change this. Let's take it up to kilohertz. Okay, there's kilohertz. We can position it. All right, so well, we can pick any arbitrary point on the waveform. Well, let's just pick the peaks because it's easier. So at 1 kilohertz, we expect about the period to be about 1 millisecond. So if I'm off here, I don't know if you can even see that, but that's 50 microseconds, 100, 200, 500. So at 500, I know I should be able to see probably at least 5 or 6 full copies of the waveform. And this is because I know that 1 kilohertz is about a millisecond period. It's the inverse of it's the reciprocal of the frequency. And then looking for the voltage input over here, this is set at about 1.5 volts peak to peak. Scale here, 500 millivolts per division. So that should be about 3 divisions or so. So there's 1, 2, yeah, just about 3 divisions. It's 1.56 volts peak to peak, it says here. So if we know that's what we're expecting, roughly, we should be able to do those calculations, set the time base to the right interval. We might want to get several waveforms at first and then zoom in on it, possibly. Okay.
Question. So it appears that the signal doesn't have a wave generator in it. Is that correct?
That's true. This one does not. This company does make them, but at the low end like this, they don't. There are, as with all companies, there are some options that you can buy with this. So the scope is $379. They make a logic analyzer attachment that actually has 8 digital channels. So you would actually see waveforms. You could see 8 waveforms stacked up along with the analog ones in time. And essentially the difference there is that each of those logic lines, there's a little comparator in the box that plugs in. So instead of seeing a waveform like this, you would actually, as soon as it reached the logic threshold, you would see what looks like a square wave, but essentially it's a logic high or a logic low. That logic analyzer adapter is about $500 as an option on a $379 scope. So that's not something I would use. If you really need something like that, you can buy a really cheap, like a 4-channel logic analyzer for under $100. It's a little tiny, like the Nano VNA or the tiny spectrum analyzer we'll take a look at. But yeah, so options are kind of the marketing thing that the test equipment people are doing now, and they're quite expensive, so can be quite expensive.
Greg K0 MGL. He said, bottom right corner looks like an alignment signal of some kind. Looks like a 1 kilohertz square wave, not a full wave generator. And
On the panel,
Say, I'm sorry?
all the way at the bottom to the right, next to the bottom right BNC connector.
Uh-huh.
Keep going to the right.
Oh, this? Yeah, that's
Yep.
this is the 1 kilohertz scope probe checker.
Yeah, it's not a full waveform generator, but it does give you a test signal of some kind to verify your probe.
Right.
Basic calibration.
Yeah, and we need to tell it that it's 10 to 1. The probe is 10 to 1. So, okay, times 1 probe. So we have a tenth the signal that we expect to see. Yeah. Am I even hooked on there? Oh, I think I'm shortened. I think I'm still shortening it out. It's a very high quality alligator clip on here.
Amazon special.
But you know what they say, it's a poor workman who blames his tools, right? There we go. Yeah, so yep, my 1 kilohertz calibrator. The wave generator, as they call it, for this guy, we could, well, let's pick a different waveform. Plug it back in. Probe times 1. There we go. I'll set it. Okay, here's our 1 kilohertz sine wave. Square wave. Now here, let's spread that out so it's a little easier to see. A ramp. Nothing like a ramp. Pulse. And you can vary the width of this pulse. Let's see, here we go, width. It's fine. I can change the width of that. So it's a pretty useful little generator. And you can buy a function generator, they typically call it, that has all these functions in a separate piece of test equipment. I didn't cover that in here. This is something that, I mean, if you're doing audio work, you might want a separate one. I had one built into the scope, but they're not expensive, or they can be very expensive, depending on how, if you have to set up a very precise pulse or something like that. But if you just need to generate audio sine waves and some square waves, you can find them for $40 or $50, $80. I saw a couple on Amazon. Again, Black Friday specials. They're pretty good. I was going to buy one, but I thought I really don't need it. So, but that's never stopped me before. And one feature that I like about this wave generator too is it generates white noise, which I've used to characterize like the audio path. I think, what was I was setting up an all-star node, and I used the white noise to take a look at the and optimize the amplitude and the band pass for the all-star controller. Okay, any questions?
So
yeah.
if I wanted to buy a scope for amateur radio use, do I need a 200 megahertz, 1 gigasample per second 4-channel scope?
It just depends on what you're going to be doing with it, of course. Probably not for most basic things. You can get a Siglent 50 megahertz bandwidth scope, which would be just fine for most things for under $200. Some of the PC hosted scopes are cheaper than that. I guess I tend to buy more capability than I need, thinking that that we'll grow into it, and that's why I kind of went with this. I like the size of it, and the price was what I was willing to pay. If that's if that's out of your budget, then yeah, you certainly could go with something smaller, and it just would depend on the application. If you're if you're signal tracing through a radio, you might find some digital pulse trains that were just too fast for a lower bandwidth scope. But if you're doing a go no go check, you may not really care what the fidelity of the waveform is. You just want to see, is it there and does it have the right amplitude? So in that case, yeah, you could certainly go with a cheaper scope.
I know Mike, K7AIH pointed out that BK Precision makes a couple real small, cheap signal generators that work well.
Oh yeah, B&K Precision, right? It's a company that's been around for a long time, and they make good and fairly inexpensive test equipment. They do make some very expensive pieces. I've been looking at an programmable electronic load for testing batteries. So, but I haven't. It's a little over, what is it? I think it's like $1,200 or $1,300, and there are some Chinese equivalents to that, little small circuit boards with a transistor and a heat sink and a little LCD display for $40. And I was actually going to get into that a little bit, but I decided not to, because mostly I really didn't want to fire in the demo area, and I was too afraid that I would either fry the thing, at home in the garage, or we'd be sitting here testing something and it would, burst into flame. So I decided not to cover electronic loads for battery testing. So maybe next month when we're talking about batteries, we can get into that a little bit. But anyway, so all right. Any other scope questions? All right, let's see what we have next. Oh, yeah, here's just an example. And there are dozens and dozens of really low-end scopes like this. So this is 100 megahertz, one channel. It's triggered, which allows you to synchronize pulse trains and waveforms. Remember, if it's not triggered, let's set that. I'm not sure how this one works. Set up. Then you won't have a stable waveform. You'll just see kind of a blurred display right here. So triggering is that's an option. When I first started out years and years ago, only the really expensive scopes were triggered, and that's something that's pretty much indispensable, is the ability to trigger at a certain point in the waveform and start the sweep going. So right here, the sweep it's triggering at this voltage level, and then it's displaying the waveform. So if we didn't have the trigger, then we'd have to have this horizontal knob. Couldn't have a detent. It couldn't be in steps. It would have to be continuous, and we'd have to tune in the old days, vacuum tube scopes. We'd have to tune the time base to stabilize the waveform, and it would still be a little jittery, but it did work. I don't know if any of you remember any of those. Some of you in the audience might remember those, but I'm happy to forget them now that we have triggering. So yeah, $82 for this Ye Pook.
So I bought an older Fluke scope meter on
Those are nice.
for $150,
Mm-hmm.
2 channel, and it was worth every penny of it.
Yeah, well, Fluke makes really nice, especially portable test equipment like that. They're great. And again, you kind of have to know what you're getting. And you know, with the Fluke, essentially, if it works, I think you're in good shape. Something like a Tech 465, you have to ask yourself, you know, can I fix it if it breaks? Because it might cost a lot if you had somebody fix it. So yeah, I've used the little portable scopes like that too, and they're great if you're on a mountaintop site. All the radar sites I work on are on mountaintops, so like, you know, like repeater sites. So yeah. But anyway, so here's just a low end example kind of for you. There was one I was looking at, another one that actually was a tablet about that big. It was a single channel scope with its own tablet, all integral. It was $140. But if I could have found a used Fluke meter like that, I definitely would have gone for that. Yeah.
Lots of them on eBay.
Really? Okay. Yeah. So buying on eBay, that's always the question, isn't it? I mean, everybody asks, can I find this on eBay? I would say if, you know, if the person's got like a 98.5% favorable rating and, you know, 1,000 reviews or something like that, and their business is test equipment, then especially if they offer a guarantee, some kind of guarantee, that's nice. It's obviously going to cost more. Otherwise, it's kind of at your risk, right? So I don't know what your experience has been with that, John. Have you found good deals, or have you ever gotten burned that way? Any of you out there too, buying on eBay?
With the PayPal guarantee, you pretty much don't have to worry anymore.
Oh, I haven't used that, so yeah. How about you out there too? Anybody bought from eBay and can recommend it, or any caveats out there? What do you think?
You can return anything.
Oh, you can. Okay, that's nice. I haven't bought on eBay for a long time, so.
Compared to the old days, they figured out everything that goes wrong, and they've come up with a program to address that so that people can buy with confidence.
Okay.
Fire protection.
All right, good. Very good. Still though, I mean, you can return, does the seller have to agree, or can some sellers?
As is, it doesn't matter because that doesn't work.
Oh.
I've returned as is stuff and gotten my money back.
Oh, you have? Okay. All right. Well, that's good to hear. Thank you. That's what I appreciate about this group. I always learn something too, always, from all of you out there too. All right. So where are we now? Frequency counters. In the old days when we put crystals into our, you know, IC22A 2-meter transceiver, and we had to net the crystals in, frequency counter was pretty much a requirement if you wanted to do that yourself. Nowadays, you know, with the synthesized rigs, probably don't use a frequency counter that much. If you're building a microwave station, that can be useful. You'll want to know if you're on frequency, you know, especially for something like moon bounce, or if you're doing, you know, one of the JT modes like that, where you have to be very accurate in frequency. So this is something you can, you know, decide you may or may not need. I bought a used HP frequency counter from the 90s. It's this guy. Let's see what we can do here. Let me just set it up, and let's put this the GPS discipline oscillator on it and see if it's still accurate. This counter has got an oven in it, so the time reference for the counter is ovenized, which it's just a really, really stable crystal oscillator, and by putting it in an oven, we kind of mitigate the problem with temperature variations in the room. So let's see if this is even going to work for us. I haven't had this on for a long time. Okay, the A channel.
Willem says the GPS fell out of the window.
Uh-oh. Well, yeah. That's okay. There's a temperature compensated crystal oscillator in there. Once it's synchronized, it'll stay pretty close for a few hours.
It's off.
Yes, my counter is off. My counter is off by
A factor of 1.
10 hertz.
10 hertz, yeah. 10 hertz and 10 kilohertz.
Oh, yeah, I could say is you get what you pay for, right? So this was like a 1993 piece of equipment. I bought it about like 6 or 7 years ago for a project. So yeah, we'll talk a little bit about calibration, because test equipment does have to be calibrated. It ages as you use it. Components age, voltage sensitive components age and they change. Time sensitive components, oscillators and things change. So we'll talk a little bit about that. Typically calibration is kind of expensive to either have done or do yourself. This little GPS discipline oscillator, I mean, this is like $250. It has other uses too. So I really like equipment that's, you know, multitasking. So I can use this in my station. I can use it to calibrate my counters, scopes, anything that is time sensitive. Because this oscillator, anyway, the specs on that anyway, it should be accurate out another decimal place or two.
You can use broadcast transmitters like UHF TV stations.
Yes, right.
Calibrate fairly easily now too, because those are all GPS-DO.
Right. Even in the old days, actually, we would use TV stations for calibration, and you know like the 60 hertz power for the power grid is also quite accurate, 60 hertz, and I forget the exact precision, but it's very accurate because when they do switching, you know, long distance, everything has to be in phase when they switch. So yeah, but TV transmitters, we've used those in the past. WWV, of course, broadcasts precise 2.5, 5, 10, 15, 20 megahertz, hopefully for a little while longer. Have they decided to keep those around? I'd heard there was a threat, but has that now been?
They talked about it in a budget meeting and then very promptly threw the idea out.
Oh, good. Yep. So yeah, and of course, ham rigs, I haven't seen it any really lately, but you remember the rigs from maybe 30 years ago had a button for WWV, so you could bring it up and use it to kind of net your equipment in. But anyway, so a counter, it's a useful thing. This counter has a bunch of features. If you have a couple of inputs, you know, like for example, if you were using it for timing a race, you could have a start and a stop pulse, and it would tell you the interval between the start and the stop pulse, for example, and a bunch of other functions. And of course, there's no screen, so you kind of have to read the manual. And I know that RTFM, read the fine manual. I have a coffee cup actually. When I worked for HP, we'd get calls about the equipment, and after a while, the call would come to me in the back room in the lab, and you know, someone would they'd ask a question about some feature, and I say, you know, that's on page 76 of the manual, and I would hear crinkle, crinkle, crinkle. Are you taking the shrink wrap off your manual? Yeah. And this was in the days when we were just starting to have electronic manuals, when they still supplied printed manuals. But yes, that's happened a few times. So anyway. Oh. I had a couple of extra slides there. I was going to talk about logic analyzers, and I thought that's a little too specialized for today, and I just didn't know if we'd have time to do that, but we can do that sometime. This was my specialty when I was at HP in Colorado Springs, was logic analysis and all their fancy plug-in systems and all of that. So my oscilloscope has has that logic analyzer feature that I mentioned. But you don't need, where's the cable? Oh, yeah, I wasn't going to show that. Instead of a external pod like that Siglent, which is $500, the logic analyzer feature, this actually was part of the scope. And there's a little pod, let me grab it. Oh, here it is right here. Out of the way. It's got lots of wires on it, so it's got to be good. Yeah, this guy just plugs in here.
Push harder, it'll go.
That's right. Yeah. So this is like a 8-channel oscilloscope that it doesn't show the actual voltage. It just tells you it's high when you're above the logic reference level for whatever you've chosen. You can choose TTL. So if it's over at if it's in the 1 region, or CMOS or whatever you want, that's programmable here on the front. So anyway, that's about all we'll talk about. I had some fun demos with the Raspberry Pi, which is what I usually show the school kids. We have counters, and we want to take a look maybe at like measuring the interrupt latency on the GPIO pins. So that's something I would use this for too, to see how much delay do I have in the software, how much delay do I have in the driver within the Raspberry Pi by programming the GPIO pins kind of as some markers. And I could look at the waveforms up here. So we'll do that another time. All right, so where are we here? Okay. So I found this little guy I saw at the Electronics Mart in Taipei at 0 to 6 gigahertz with 13 digits frequency counter for, it was $127 on eBay. It was a little bit less in Taipei. And I was really thinking about buying one, but I didn't need a counter at that point. I probably will as I get into moon bounce, just to make sure that my microwave equipment is working right, because you tend to use transverters, so you want to make sure your references are good without having to pull a scope out. But this was pretty amazing. The specs on this thing were pretty amazing for $127. So we'll have to get one and try it out. Oops. Going the wrong. Okay. Yeah. So another thing you are likely to need is an RF source, a signal generator, let's call it. And for ham use, this Elecraft kit is kind of a neat thing for your HF station, 1.5 to 200 megahertz. So it'll cover 160 meters to 2 meters, and up to 1400 megahertz with harmonics. So it is digital, so it is a square wave, but like the GPS oscillator that I have. They claim 50 parts per million stability. That's not too bad. Yeah, it is. Also, they claim pretty low phase noise. So phase noise essentially is how stable the waveform is at a given frequency, or does it tend to jitter? Does it move a little bit? I mean, that's kind of a good way to think about it. And it's measured in dB with respect to the carrier per hertz of the carrier. So 105, that's pretty decent phase noise for such an inexpensive thing. Okay, yeah, preset frequencies. It's a sweeper in there. So if you need to, and you can program it with a computer. They have a little piece of software that plugs in. I think it uses a serial port. Yeah. Oh, USB. Okay, or RS-232. So I don't have one of these. Does anybody have one? Has anybody played with this? No, okay. Yeah, so it's $270. It's a little pricey, but definitely tailored for ham use and should be useful. Okay, so here's another one from this this group that made the frequency counter. So it's their WB SG1 signal generator. Again, this thing goes up to 20 gigahertz. They claim 20 gigahertz. I'm sure it's based on one of the new like direct digital synthesis chips. So a lot of these test instruments are possible because some of the chip makers, like Analog Devices, they now make synthesizers on a chip. They make direct digital synthesizers, all kinds of RF components that are on a chip. Programmable oscillators, things like that. Some of you may have worked with those before, but the manufacturers publish a reference design, kind of like, what can I do to get this chip going? Here's a circuit board layout. Here's a basic circuit to make this oscillator work, programmable oscillator. And then people like this company will take that chip, make a board up, tweak it, maybe add some other things to it, and they'll take advantage of the capabilities of that chip. So, back in the old days, designing a piece of test equipment was a pretty laborious process. You had a lot of physical environmental things like temperature. You'd have to compensate for temperature and all kinds of other effects from the outside. But now things are on a chip, very repeatable. It still makes me wonder, though, if maybe there's some cases where this thing would be, maybe it's got spurs. Maybe I don't know. I haven't looked at the spectrum of it. So this one's $329 at thanksbuyer.com, which I had never heard of before. But that's including shipping from, I think, Shenzhen, where they make them. I don't know. It looked interesting and it looked like an option. Question?
Yeah, there was just a couple. I'll go back just a little. I know Mike K7AH pointed out that for test equipment, you can also look at used rental equipments, test equity, Electrotorn, etc. They sell used equipment for great deals if you can catch them at the right time.
Yep.
And then Glenn Hetchler, he said he has an XG3S and it does not have modulation, but he wishes it did.
Yeah, exactly. Yeah. And I have let's go here forward here. Oops. We looked at the GPS discipline oscillator. We already talked about that. So here's a kind of a staple used Hewlett-Packard signal generator. It's 100 kilohertz to 2100 megahertz. These are, typically just kind of surveying eBay. They're a couple grand, but they have a full complement of these analog modulation and phase and pulse modulation. So AM, FM. Again, really low phase noise, so you can get accurate measurements. One of the best things about this analyzer is the attenuator in it. And you can, in 1 dB increments, you can get a really low level signal. I mean, down to minus 127 dBm. So that's really tiny. So this would be great for testing receivers, things like that. You could conceivably do that with a couple of attenuators, fixed attenuators on the output. But this is the one that I've seen most often among the microwave enthusiasts and moon bouncers, who tend to be also microwave enthusiasts. Yeah, B&K probably has. It's been a while since I've looked at their RF signal generators, but I know I have seen B&K generators with AM and FM capability. Is that? I mean, would you be looking for a person who asked about that? Would you be looking for more than just AM, FM, and maybe phase modulation? something digital. I mean, once we start getting into the digital realm of modulation, then you're looking at much newer equipment. You know, if you're trying to simulate or like test, for example, DMR radios.
It's an order of magnitude more.
Yeah,
than trying to buy anything.
yeah, quite expensive. I did a couple tests. I wanted to see, you know, like for example, with the spectrum analyzer, if you take your analog 2-meter UHF radio, you can see the deviation. You can see the sidebands on the spectrum analyzer. You talk, you can see them moving, you know, as they should. Amplitude of the modulating signal goes up, the deviation increases. And I thought, all right, so DMR radios are digital, but they basically, they're feeding this similar kind of FM modulator. And there's so much back and forth, so much burstiness that, you know, the DMR radios are sampling the audio and then they're sending a 20 millisecond burst and then turning it over to the repeater, to the other station. So they're always, you know, time domain sharing pulses. And if you try to look at a DMR radio on a spectrum analyzer, what you see is essentially the carrier and some sidebands that are jumping up and down as that thing pulses. And so with any of this older equipment, analog-based equipment, I don't think there's really anything you can do. I mean, you know that it's making power. It would be really hard to measure that power because it's a pulse system. So, you know, the radar equipment that I work with is pulsed, and we have special pulse power meters where we can actually characterize the pulse, and in order to get a peak power measurement. But they're quite expensive, and typically not something that hams need. I mean, if your DMR radio, there's really not much adjusting you can do to it. If it's not working, you know, like Willem's Baofeng, you just find a tower to drop it off of.
James just pointed out that the WB SG1, it looks like there's one on eBay for about $150.
Oh, okay. Yeah. Yeah, I'd have to get budget though from the comptroller at home before I could do that, and that's so I need to choose my toys carefully. She has not completely sequestered my toy budget yet, but since I've retired, but I do think about that before I go off and spend. I bought a few things, and I bought this scope. I bought some some other little piece of equipment we'll take a look at here. Some of these little handheld, the tiny spectrum analyzer and the nano VNA. So that pretty much took my budget for the month. So let's go on. Yeah, power meters. Oh, where'd the picture go? Sorry, I had a picture there. So MFJ makes this peak reading watt meter. Wait a minute. No. I'm sorry. I don't know how that got in there.
So that meter requires a battery, and the battery's always dead when you need it.
Oh, the Bird 4410? Yeah. I mean, I had a Bird Model 43, which needs separate slugs, and I've got a small collection of them, and they were, you know, they had to save up for those. But yeah, the 4410, you know, 7 ranges for each of these elements, these slugs. So the Bird meter, essentially, there's a connector here, typically an N connector, but you can have other options. So this is I think it's like a die cast and machined pass through here with it's kind of, and the slug sits in the path, and there's a diode in the slug, which then drives the meter. And this one actually has an active circuit board in there, an amplifier to drive the meter. So when you change frequency, you have to change the slug because they're tuned for that cavity in there. And those things can get pricey. And the Bird meter's been around for a long time. The 43 doesn't have this little multiplier, you know, range multiplier or whatever. But yeah, I've heard that too. The batteries are almost always dead, and you have to take the back off. But you know, you see these. Some people like them, but it's been around for so long. You know, that's why I put it in. Okay. Now for a station monitor, these telepost post digital vector watt meters. This is pretty cool. I mean, if you want to have an impressive looking watt meter in your station, there's a sampler, remote sampler that fits in line transmitter to load. The load being, you know, the antenna or amplifier or whatever, but usually the antenna, and they'll measure SWR, they'll measure impedance, resistance, phase, and reactant capacitive or inductive reactance. Pretty fancy. So you can spend all your time monitoring all your antenna impedance while you're trying to talk. It's pretty cool though. $475 with the 3 kilowatt coupler. So I don't know. Has anybody used one of these? I mean, I wanted one just because I like the display. You know, it's like the guy who said, yep, this Cessna 150 has more knobs and buttons and controls than any other Cessna 150. I glued them on myself. Okay, so yeah, among the microwave enthusiasts, these older HP power meters are really popular. Yeah, when I was a summer hire years ago, we had 432s were pretty much everywhere on all the benches, and they're not that expensive. The actual meter part. So the 432 that's been around for 30 some years, about $99. 435, I found one for 30, and then when we got the digital meter, that was really fancy, $95. But of course, that's only the start. That's the cheapest part. These sensors, and there's a ton of them.
And a lot of them have been used as fuses.
Yes, they very often get fried. So these sensors are they're what we call a bolometer. So a bolometer measures power, RF power, by heating an element inside and looking at the temperature change. So if you have a certain amount of RF power, you know, if you have 100 watts going, or say 10 watts going in, then that would heat the element to a certain temperature that could be detected. And then there's corrections in there for, you know, for ambient temperature and for the frequency response, you know, of the connectors and things like that. There's a calibration chart that's on the top of the sensor, and the calibration factor you have to enter in on a knob here, or here, or digital cal factor here. And that these things are very expensive, and because they have heating elements in them, yeah, they're very often, when you find them, if you find a cheap one, it's probably dead. Yeah. Personally, I've only fried one of them. So yeah, that was the day when I blew up about $10,000 worth of impact diodes too, that we're trying to make a solid state 9 gigahertz transmitter about 35 years ago. But before that, it's easier now a little bit, but we use these impact diodes, these little diodes about the size of a grain of rice, 6 of them in a cavity, machine cavity. And yep, if the cavity went out of tune, then all 6 of those devices at about $1,200 a piece fried. And that was about the end of my first week as a student summer hire, sitting at the bench, looking at the RF output waveform. It was humming along. It was making about 50 watts at 9 gigahertz. And the department manager walks up behind me, and you know, it didn't surprise me. I mean, he was coming up, and he said, "How's it going?" "Oh, you're working on the combiner." And I said, "Yes." And I reached up to set the scope, and the trace went flat. And he goes, "That's going to be coming out of your paycheck for a long time." And then he said, I've done that myself a few times too, so don't feel badly about it. But it made me feel really bad. You know, it's my first week. I'm a student, and I've already cost the department a huge chunk of money. But that's kind of one of the hazards of the industry. But we had a lot of these HP power meters, and the sensors. They're great. They're really accurate. They're great for microwave. They're nice because they run at higher frequencies. You know, you could conceivably use this for measuring your station power, but this is really better for. Yeah, you would. I mean, you're looking typically at plus 20 dBm, so 100 milliwatts max.
I have one of the newer ones, the digital style, and I have two 200-watt 20 dB pads to go in front of it, so I can measure more reasonable power levels. Yeah, exactly. Right. So, right, a pad is an inline attenuator, so it's impedance matched so that the frequency response will be somewhat level, somewhat flat, and I have a picture of my friend's microwave bench, and he's got a higher power attenuator in line there. And we've all used these. I mean, I have to put these things in. They're not that accurate particularly, but they will tell you whether your antenna is performing or not performing, maybe. Yeah, yes, exactly. But yeah, and they've gotten a little expensive too. I remember them being cheaper, but it's probably been 20. No, I'm not even going to say it. I'm dating myself. But anyway, I just put it in because we've all used them, and you certainly might want to consider it as a check. See if you're in the ballpark. And I found this. I saw this in Taiwan, in Taipei, and I've tried to put things down that if I could find them on Amazon, just in case somebody is interested in picking one up. In this case, Banggood, which is another site that ships directly from China. I have no idea how good this thing is, but the specs are awesome, really awesome. Oh, that's another thing about test equipment too. Even the big companies, HP or Keysight now, and Tektronix, they're in kind of a spec war, and so you always have to kind of read the specs carefully and take them with a grain of salt, because they'll claim lots of things which can be true, but at the expense of other parameters. So they might say they have phenomenal accuracy, but there might be some other parameter that's kind of let go by the wayside. So with this this power meter, I mean minus 45 to plus 5 dBm. So it's obviously using probably a chip from Analog Devices or some clone of that. 8 gigahertz. So yeah, I don't know. I just thought it was interesting that and they claim it'll measure 1 nanowatt. Now, 1 nanowatt to 2 watts. That's a lot of range. That's what it said. 1 nanowatt. Yeah, a nanowatt is not much power. I mean, you can't really even measure a nanowatt with those HP sensors, and they're pretty good. So yeah. Yeah, for $38 though, I mean, it would make a nice. You could put it on your shelf. It's a little decoration or something high tech. Anyway, but this is an example of a piece of equipment that I've seen on my overseas travels that I probably wouldn't invest in. Okay, another thing, antenna analyzers. That's how are we doing for time? You're looking at the time. 47. We're going to do 45 minutes.
Okay. All right, we'll go for a few more and we'll see. Antenna analyzer is kind of a luxury, depending on your station. This is more useful for HF stations. Typically you'll use a network analyzer or something like that to
characterize your antenna at microwave frequencies, but everybody used the MFJ, what was it, the 259? There's one with the little analog meter. Those were all over the place. I never used one, but this is their new digital one. $340. 1 to 60 megahertz, measures the SWR, resistance, reactance, and impedance, plus 5 dBm. And it looks like it's made to be dropped. That's all I can say. Hopefully without, made to be held. And I don't know if you could drop it off a tower, but it looks like it's made to be dropped to me. Anyway, so I hadn't seen this one, and I thought that was kind of interesting. And then the rig experts, that's kind of the Cadillac of antenna analyzers. I've not used one myself, but these all use pretty much the same technology. And again, some of these modern chips from Analog Devices, synthesizer chips and detectors, and kind of all integrated on 1 or 2 chips, make these possible. They just add their display and firmware. Oh, okay. Yeah. Would you use this on a tower or no? Okay. So I thought here the one that covers 6 meters, $265. They do have a 1.5 gigahertz one for $900, which is kind of cool. Yeah, 1500 it says. I've seen the 1400, and then I just noticed the other night when I was putting this together that the 1500 megahertz version too looked pretty cool. So I don't know, anybody have opinions about antenna analyzers? Have you used them? I've never spent the money, but I've kind of wanted one for a long time, and
They're handy and fast to solve a problem.
Yes.
But there are devices out there that are meant to do nothing but antennas.
It's hard to hear you, John.
They're commercial. Here, Dean's got to walk closer to me so you can hear me.
Oh, sorry.
There are commercial grade devices out there like the Anritsu analyzer called a Wiltron. I prefer them because they're fast, but these are great for hams. They're great for hams.
Yeah, I have a couple of examples too of the Anritsu boxes, but I wanted to bring this up just because it's a useful thing, and I've always wanted one, so maybe one of these days. All right, now this was kind of a cool thing that I saw this in Taiwan. I ordered this one on eBay. Let's see if we can do the unboxing here. Does this work, Mark? Can we? We'll do the unboxing. It comes in this really cool little box with the gold lettering on it for $70. Quite a deal. Here we go. So yeah, it's are we here? Oh, here. Okay. Yeah, it comes with it's got the USB-C power cable. It's got opens, shorts, loads, which are nice for calibrating, and a couple cables. So we can turn it on. I wanted to try to tune this duplexer that John lent me, and I'd set a bunch of presets up, but I lost them this morning when I turned it on. I don't know, I must have zapped it or something, but I lost the presets, so I think it probably would take too much time to go through all that again. But I'll show you the display. It's pretty cool.
Turn it 180.
Oh, sorry. You're right, I forgot. It has to be this way.
So you can see it.
You move it a little bit. There you go. Okay.
Push it away from you.
Okay, there we go. Yeah. So this thing's pretty small. It's got a 4-inch LCD, but this actually is a vector network analyzer, and so network analyzers work with 1 or 2 port RF devices. So it has 2 ports, and port 1, well, they call it 1 and 0. So the measurement, this gets a little detailed here, but you if you're measuring, let's say you want to characterize the frequency response of a filter. So this thing has got it's got an RF generator in it. It's generating a swept RF signal. It tracks with the display, and you could connect a filter to it, and it will measure the power from, it'll put power on this port through the filter, and it'll receive it on this port. So port 1 to 2. So this is an, or I'm sorry, 2 to 1. So that's an S21 measurement. Yeah.
Many people that understand RF may understand S11, S21.
Yeah.
It's a little cryptic for people that haven't seen it before.
I had a bunch of slides on this, and I took them out just because, I mean, we've kind of been down that rabbit hole. We use this a lot for RF devices, but essentially you have a generator, a stimulus providing RF energy. You have a device under test, like a filter or even an amplifier, and then you have on the other end you measure you can measure the power and some other characteristics of that. The device can also it can look at power coming back, so it can see if you have reflected power, which is usually not desirable, but you want to measure it. So port 1, I don't know why they call this channel 0, but an S11 measurement is power out of 1 and back into 1, just to really keep it simple. So yeah, reflected power, and 2.1 is power through the device. There's actually S22 and S12, all the permutations of that, which most of those are pretty specialized, and you might need those if you have microwave components like amplifiers on a circuit board, amplifiers, other active devices, filters, those kinds of things. You might characterize parts of those. That would be very specialized. Basically, those antenna analyzers that we just looked at are network analyzers like this that are specialized to look. I mean, we have an antenna. An antenna is a one-port device. S11. What's the power going to it, and what's the power reflecting back out of it? So antenna analyzer is just a very special case of this guy that has a much easier to use interface on it. Yeah. Okay, so let's see. Yeah, again, since all my presets got erased, I'll talk a little bit about you can look at the menus and things a little bit here. So this was designed by a fellow in Japan, and they're manufactured in China. It's really got a lot of capability for something that's $70 to $100, something like that. Depends. I mean, if you buy it Amazon Prime, it's like $95. Gigaparts listed it for $70. I found the other day. So this will measure. It'll measure the impedance. It'll measure capacitive and inductive reactance, frequency response, and then for those of you who are extras, you had to know a little bit about the Smith chart, which is just a way to plot the AC circuit parameters like impedance and capacitive and inductive reactance. So I'm not going to get into that. As I said, I had a bunch of slides, and I thought that would be a little too much because some of us work with that, some haven't. So this could also be used as an antenna analyzer. So maybe I don't need a rig expert, but I'll need to figure out why I zapped a thing and cleared it. The controls are kind of small, and I have big hands too, so I mean that might be part of it. Anyway, this is a really capable. This is an example of a piece of test equipment that when I started out, years and years ago, this was very expensive. I mean, you're talking $200,000 and big, heavy piece of test equipment, easily a couple $100,000. And now for $70, we have most of the capability. Now it doesn't update as fast. It's not quite as accurate. It has some limitations that the big fancy one, and they still make those. They're a little bit cheaper now, but they're still tens of thousands of dollars. But for ham use, if you were making filters, let's say you were designing bandpass filters for field day, and you wanted to make some of the more popular designs, you might use this to tweak it while you had it open, the inductors, capacitors. And this would be a really good tool for that, where antenna analyzer probably wouldn't be, because field day bandpass filter it's a 2-port device. Here, in fact, I have one. So we use these at field day bandpass filters. So this one's for the 20-meter band. When you put this in line, when you're operating on 20 meters, and it would filter out harmonics on the higher bands. So this is what we call a 2-port RF device, because it has 2 ports. This one happens to be, it's all passive. There are no active amplifiers or anything. It's all just inductors and capacitors. So it doesn't matter which way you hook it up. It doesn't care. There's not an input and an output, but it is a 2-port device. And so if you were to connect it to the vector network analyzer, you could characterize the frequency response of this, and you could look at mismatch in the cable between them. And then that's something you would do pretty much when you're designing. Day to day, we have other ways to look at that, and we'll take a look when we do spectrum analyzers here in a second. We'll put this on the spectrum analyzer and have a look. So questions at this point? Okay, all the S11 and
that from previously, I'll throw out Mike K7AIH was pointing out that SiteMaster is another tool for using for sweeping antennas, and he pointed out that he uses his SiteMaster regularly.
Yeah, that. And I have a SiteMaster slide coming up when we talk about spectrum analyzers, because that's kind of in that genre. So let's go there. Yeah, so this vector network analyzer is a great design tool. I mean, if you're really down in the nitty gritty of the designing something and trying to make it work. So, for somebody who's been an RF person for a long time, this was cool to see for $70, and I had to have one. So we will we'll discover and work through it and use it. I'll have to come up with a good project to make, and maybe it would be good to make a training video or something like that.
We have RMHAM Tech Talks for that.
That sounds great. That sounds like a great idea. That'll teach me. All right. So spectrum analyzer is it's essentially it's a receiver, really, that where the local oscillator is swept in frequency. So it's like a receiver that lets you panoramically look at the spectrum from some frequency DC to blue light up here. It's actually not, they don't actually cover that range, but from in some frequency range. So this might be like the 20-meter band, or this might be the FM broadcast band, for example. And again, the explosion in really inexpensive RF chips, a lot of that for the cellular industry, for example, that's really driven a lot of these designs. So you get, somebody who's interested has been interested in RF design, and they learn about these chips, and they immediately think, what can I make with that? So, I have boxes and boxes of parts like that. So what you need is time. That's the critical element. So anyway, this RF Explorer comes in a few different models that are optimized for different frequency bands, but it's pretty cool. 50 kilohertz and 960 megahertz for this particular one. They make versions that are optimized for like the Wi-Fi frequencies, 2 gigahertz and higher. I think they go up to 6 gigahertz. So you could use it to, take a look at your Wi-Fi propagation. They've got a nice little display, little LCD display. It's not too high resolution, but it's great for handheld operation. But the cool thing about this, it's a PC hosted instrument, but here's a case where if you're walking around just looking for RF leakage or something, this display would be enough. But they do give you the PC application, and it presents the spectrum. They keep the time element here and show you the waterfall, which is nice. Kind of a neat thing. And again, it's relatively cheap too. I mean, I'm used to all these things costing tens or hundreds of thousands of dollars, and that's what's really impressed me lately. All right, so let's see. Oh, a friend of mine, Doug Millar, K6JEY, is a big microwave guy. I've had some really great conversations with him about that. And he was able to use a Fujitsu low noise block converter, and you can see the 10 gigahertz waveguide flange right there. He was able to down convert that. You need a bias T to power it. So this just injects DC power that powers all the amplifiers and oscillators in here. So he essentially made a 10 gigahertz spectrum analyzer. These LNBs are about $20 used. Bias Ts, they vary. You can make your own, or you can find them surplus for a few dollars. But this is pretty cool. So this extends the RF Explorer out to 10 gigahertz. And you can use the same technique with other spectrum analyzers as well. Spectrum analyzers that go up to, say, 26 gigahertz are not uncommon in the used market. HP, they're still kind of expensive. They still can be a couple grand. We'll take a look at those. So here's a way, if you were making a 10 gigahertz station, you wanted to see if if your signal was fairly clean, you could use this. Okay, here's the Cell Master, the Enritsu. Fairly, well, they're fairly expensive. The nice thing about them is they are portable, and we also have the Spectrum Master here, so that's coming up. But the Cell Master is a little bit cheaper than that. $800 used. That's a lot of money. You'd need to be into it. But then again, some of us spend 10 grand on our HF rigs, so it's all in what you're interested in. I've been interested in microwave. I've carried Spectrum Masters pretty much on every trip overseas for like the last 10 or 15 years, and I love it. They're great, up to 4 gigahertz. We actually built one of these into one of the radar systems, and I wrote software drivers for it to pull the waveforms off and integrate it in with our monitoring system for maintenance. So every so often it takes a look at the transmit waveform and spectrum and records that. So when we go on site, a couple times a year. We can pull those waveforms up. If the customer said, we had a failure at a certain time, we can go back and look at the waveforms, and we can see, was the transmitter degrading? Was there a problem with it? But yeah, these are a little expensive, $1,800 to $4,500. I don't know. Have you bought? Any of you bought any of these lately?
Not lately.
Okay.
The last one I bought was 20 years ago.
Okay. Well, it's a very solid piece of equipment.
Doug had bought them.
Yeah, they're very nicely set up, very nicely laid out, easy to use, and it's easy to get a good measurement, a good solid measurement that you can trust on it. So anyway, I'd love to have one, but that's all right. Well, that's good to know. Okay, so spectrum analyzer it's a nice thing to have for characterizing equipment, taking a look at your transmit spectrum. this company Regal, and from what I understand from their website, that's the correct pronunciation. It's not Regal, it's Regal. So for whatever that's worth, they made this digital spectrum analyzer 815 with the tracking generator. So tracking generator essentially is just, it's an output where as the spectrum analyzer scans in frequency, so this is the lower frequency, this is the higher frequency up here, you actually get an RF signal that's at that frequency at exactly the same time. So when it's, you know, here in the middle, if this is 750 megahertz, then that's what's coming out of this jack. So it tracks with the spectrum analyzer as it receives. So here's the spectrum analyzer input. It takes whatever the measured power is at that given frequency, and it plots it. If you have a stronger signal, more power, you get a peak, and it drops down like that. So let's see. Probably one of the things that you need to think about with the spectrum analyzer, the number one rule, marked on the right underneath the input jack, typically there's a little sign that says damage level. This is very important because this jack, the signal is usually going into a microwave mixer, and that thing can only handle a certain amount of power. In this case, it's plus 20 dBm, which is about 100 milliwatts. If you put more than that in, you know, you're essentially going to damage the diodes in that mixer, and then the thing will be pretty much a fishing weight, doorstop, boat anchor, whatever. So always watch the damage level. Like on the scopes, you need to watch the max voltage level. Let's see. Okay. Another important characteristic on a spectrum analyzer is because it's really a receiver that receives over a wide range of frequencies and then plots the amplitude of the received signal. You, as the signals get, you know, weaker and weaker, you eventually get to a point where the components inside are actually generating noise. And the noise level in this case is about 135 dBm, minus 135 dBm. That's not too bad. The HP spectrum analyzers are a little better than that, but you pay a lot of money for that. I've seen some reviews of this where people have claimed that it doesn't really go down that low. So the lower noise floor for this thing, the detectable signal is not really that low. It's possible to get it this low with some settings on there, but that may not be useful. Then the analyzer may, as you begin to narrow the bandwidth to pick these peaks out, this has to track more and more slowly. So to get a real low noise level, you might need to, this might take a minute or so to track across there, and that wouldn't be too useful. So technically that's right, but only under certain conditions. So I have one of these. They were $1,500 when I bought mine, and I just noticed Amazon Prime and the Regal website, they've dropped it to $9.99 now. So that's pretty cool. So let's set the spectrum analyzer up and see what we can see. Use that. Where'd he go? Here he is. Give it a second to boot up here. Okay. Oh. All right. So no, it's not actually. It's my microphone. There we go. There's a real life example here. Let's see. Do the tea hunting trick. Can I use body shielding or we're too close? Yeah. So the first thing anybody seems to do with a spectrum analyzer when you first sit down and play with one is you stick a piece of wire in the input jack and you look at the broadcast band, which is always fun. So this spectrum analyzer has an auto feature, which is kind of nice, where it'll pick the strongest signal it can find. It'll center that, and then it'll decide, it'll give you it'll look a little bit off to the sides. So the center frequency is 566 megahertz right there. And I think it locked into this. Is that about right?
Yeah. What's the actual frequency on the yellow one? It shows on the display. 610. 610? No.
It says 566.55.
Yeah, 566.5. Exactly.
Oh, well, there we go. See? It'd be interesting to see. All right, so let's, we can set the start frequency. Let's set it at 85 megahertz. And the stop frequency at 108 megahertz.
And we're right below lookout, so it should be very hot.
Yeah, all right, now we can turn a marker on. Let's see, where's the marker? Where am I? It's hard to see. Marker 1. All right. I don't know if you can see it here. Let's see. So when you're looking at a spectrum, there could be several peaks. You may want to know, you may want to remember where that is. You may want to know what the frequency is there. So they provide 4 little markers, and this is kind of jumping around. You can see, let me see if I can move it over here. The marker says number 1, and it's on this peak right here. So this is telling me that the marker is at 103.63 megahertz. And it's probably 103.5. I don't remember what station that is.
It's on lookout. It's on the channel 2 tower.
Yeah. So let's see. Let's go down here and see if we can see what this one is here. So this is obviously the FM broadcast band. A nice source of signals, a nice spectrum of frequencies. 95.9. Let's call it. Yeah, that's. Okay. Anyway, so this is okay. So that's a spectrum. There's a lot of RF energy, lots of frequencies. We could look at this goes down to 9 kilohertz. So this is 9 kilohertz to 1500 megahertz. So let's go down to the AM broadcast band and see if we have enough of an antenna to pick anything up. So let's we can choose frequency or amplitude. Let's set the center frequency at 850 kilohertz. Yeah, need a little bit more antenna, but yeah, you can see some activity there. This is really too small an antenna. All right, so what else can we look at? Let's take a look at the GPS discipline oscillator, the 10 megahertz. Let's see how clean the spectrum is on that thing. And I know it's plus 10 dBm, which is 10 dB under the damage level, so we should be okay. Let's let it find it. Yes, I know I'm way off, sorry. You know what? Yeah, it's below the damage level, but it's actually too much signal. Let me grab an attenuator and stick it in line there. I'll put a 10 dB pad in and see if that helps. All right, so when you work with, especially with on radar systems and probably radio systems, you always end up with a great collection of adapters. Here's N to BNC, which I'm using here, N to SMA. The SMAs are, if you get good ones, are typically quite expensive. I don't know how familiar people are with connectors and things like that. I thought about putting a little unit in on those, but most of us know we know the connectors on the back of our radios, the SO239 jack, the PL259 that's on our coax. Some of us use N connectors. These are good for a wider range of frequency. And 1500 watts. Yeah. BNCs are 500 watts. Yeah, and maybe 500 megahertz. Realistically, they'll go higher. The thing about them is they're convenient because you don't have to screw anything in. You just plug it in and give it a twist.
Bayonet naval connector.
Well, that's one. That's one definition of it, but I've heard others too. One is British Navy connector. So yeah, I'm not sure. It's kind of lost in the midst of time. What's that? Oh, a C connector?
Yeah, it looks just like a PNC, but it's bigger.
It's bigger. And then there's also a threaded version of the
TNC.
called the TNC, threaded NC, whatever that is, naval connector. And then, yeah, pardon me a second. Let me grab a connector. Okay, yeah, let's take a look at this too. So this is an SMA connector. 5/16 inch wrench is used on that normally. So it has a pin, a female pin like that. Male pin,
The male is on your
this, yeah. So it's a plug. You look at if it has a pin in, it's a plug, and it doesn't matter. These are standard SMA connectors. Some Wi-Fi equipment and other things use reverse polarity or reverse where they RP SMA, where this one would actually have the socket insert, and that one would have the thread on the outside with a socket, and the equipment would have the opposite that fit together with that. So anyway, these are SMA. These are quite old. I've had these a long time. So
they don't usually go back.
These are typically good to 26 gigahertz. So that's why they're so expensive. All right, hey, there we go. Yep, we had a little bit too strong a signal for it. Amplitude. Okay, yeah, it has the analyzer has an internal 20 dB pad, which it put in there as well. So take a look here. I told it to put a marker on the peak signal, since we have such a clean signal. Right there it is there. And it looks very, very clean. Now we could zoom out a little bit. Let's look out to 100 megahertz. Oh yeah, okay, there we go. We got a few harmonics. Actually, quite a few harmonics. So yeah, there's 10, 20, 30, 40, 50. So again, the odd harmonics are usually what we see expressed. So the third and the fifth harmonics they're actually pretty high. So that's. I mean, that could be useful for testing. The I think the injection board has filters on it, so if we needed to, we could filter out these other harmonics with a filter.
There's not a lot of filtering in that.
No, nope. But this is also a way I could calibrate my spectrum analyzer too. I have what I know is a 10.0000 megahertz signal. Okay. So what can we do with the tracking generator? Let's have a look.
Yeah, before we get to the tracking generator,
Yeah.
just kind of looking through. I mean, everybody may want to look at some of the chat. There's been some pretty good comments. I won't. I think everybody can read, so you can kind of go through there. I'm just going to kind of pick out some of the questions, and I know there's one from kind of where we're at now from George W0NFW. Do most of these spectrum analyzers have a summing function over a settable number of sweeps? Packet transmissions such as Wi-Fi will not show spectrum usage / activity in single sweep mode.
Wi-Fi is too fast in most cases. Most Wi-Fi transmitters are too fast, and the spread spectrum pulses too quickly for a regular spectrum analyzer to see it.
Yeah.
It takes some fairly expensive and fairly specialized equipment to be able to do that. And it's not something that a normal experimenter is going to have access to, because it is an order of magnitude more expensive than most of the equipment.
Yeah, at least. Yeah, it will do averaging. There's some math functions like that, but yeah, in general, it just doesn't respond fast enough for that. That's a really good question. Yeah, when you start designing, in those realms, then yeah, you're spending some money. Your company's spending money. Anyway, what other ones we?
Like I say, there's a bunch of comments that I won't go through, but there was another question previously from Ted Klein in Zero RQV. The $200 RF Explorer WSUB 1G Plus, kind of compare that versus the $20 RTL SDR dongle. Is there a lot of difference, or is it just mainly more bandwidth?
Well, I think the dongle has probably more bandwidth, but it's incomplete. The RF Explorer it's a complete solution. They've got a display, they have controls for the frequency sweeping, the frequency ranges, filtering and those kinds of things. Whereas the SDR, the dongle is basically just digitizing the RF, the RF signal, and outputting it on a USB, and then you've got to do digital signal processing to recover a signal of some kind. You do have the flexibility to use like the GNU radio tools, which will let you connect the output of that dongle, and then you can build sets of filters and essentially build a spectrum analyzer that way. But RF Explorer's already done that for you. So yeah, there would be there'd be a lot more flexibility, but that would be something for an experimenter, really. But that's a good question, because essentially the RF Explorer is really doing what the dongle's doing. It just has more stuff on the back end and a display. Yeah, that's good question. Okay, how are we doing for?
Yeah, if we want to, do you have some more slides? We'll kind of, maybe 10 minutes. Maybe we want to wrap it up. Unless, then we take a little, there's some more time for questions, or, go ahead and come off mute, and feel free to ask some questions directly with Dean.
Well, then if we're going to, I don't even know what time it is. That's 11:30. Oh, I'm sorry. Okay. Yeah, I just wanted to show the characterizing like a field day bandpass filter, and then show the tiny SA, which is the next slide. And then we can call it you can just call for questions. So be okay with that? So yeah, let's use the tracking generator, and let's take a look at the bandpass of this filter, for example. So this would be spectrum analyzers lab type always have N connectors like this or SMA connectors. There's some other, there's another kind of connector called an APC7 and a smaller version, APC 3.5, that are flat up to 26 gigahertz. And they're used on some really high-end test equipment, but I've never seen those on anything, you know, that's less than about 50 grand. All right. Tracking generator. Yeah. All right, so when we do a measurement like this, the first thing we need to do is to correct out the losses in the cable. So we're going to use these cables to connect to the filter. First thing I'm going to do is put a barrel connector in, and of course, there is some loss in the barrel connector, so there'll be a slight inaccuracy here, but we call that normalizing. So we're going to normalize this. The analyzer passed the signal through, swept through it, and now it's corrected out the loss in the cable. And then we can connect up this is a 20 meter filter, so let's see if this looks like the 20 meter band here. Oh, here we go. So let's set the frequency. We'll set the start frequency at, call it 1 megahertz, and the stop frequency at 29. And then I'm going to move the marker. So let's see, this peaks at 13.3, if you can see it here, to about 14, that's about 15 megahertz. So 13.5 to about 15 megahertz is the top of the bandpass for this. And it begins to drop off as you go higher in frequency. And the idea is that if you're operating on 20 meters, you don't want to clobber the 10 meter station. So, you know, at 28 megahertz, 28.5, there's at 21 megahertz. So on the 15 meter band, we're looking at, what is our, so there's 10, yeah, it's about 20 dB down from the band pass. So there's about 20 dB of attenuation on 15 meters. So that'll help the filters in the front end of the receiver, you know, just that much more. And yeah, 28. We're looking at 10, 25, almost 30 dB. So these do help. So anyway, I just wanted to show that if you can see the waveform there. So this is useful. I brought a demo too, but I don't think we're going to have time to do it. So this analyzer can be used with a return loss bridge. Yeah, go ahead.
Chris Keller says, my HF radio has a built-in power and SWR meter. I also use an external dual needle watt meter / SWR meter. Sometimes they're quite a bit off, say 30%. How might I measure which one is more accurate? Would an oscilloscope do the job?
No. Oscilloscope wouldn't do that because you need a SWR meter needs a way to sample the RF going both directions. Yeah, because the bird watt meter, remember we showed that little machined cavity inside. The element that is sampling, it can be turned 180 degrees. So it can measure power going one way or power going the other way. So that would be probably the most accurate way to do it. Yes, with the correct slug. Yeah. So anyway, yeah, to measure, and I'm not going to set this up, but I'll just show you what I'd set up. I have a little 2-meter antenna on a hastily constructed ground plane. Return loss bridge essentially does what we were talking about, the bird meter does, power going one way versus power going the other way. So you have the tracking generator would plug in here and provide RF out to the antenna, and then any power coming back would go into the spectrum analyzer, and this spectrum analyzer actually will do the math looking at the power going out and the power coming back reflected and plot the SWR on a graph. So I won't set that up now because we're running out of time, but it is possible to do that. And then the last thing I wanted to show is this little guy. So this is essentially a complete spectrum analyzer like this bigger one that's it's got a little 2.5-inch LCD display. Let me just put the broadcast band antenna in here. It's already found a peak at 104.1. And here, this is the spectrum display. So essentially the same as this benchtop analyzer. This is not the way that the tiny spectrum analyzer is made. It uses switchable resolution bandpass filters. It does its calculations and its measurements in a little different way. So there's some limitations. There are also some known known leakage, RF leakage at like 40 megahertz or so. You have to watch out for. There are a few gotchas. You need to read the instructions carefully, but for a little pocket device, it be a good monitor, and it just seemed like a cool thing because it's so small. I like little tiny miniaturized things like that. So anyway, another toy. Really fun. All right, so do we want to go to any other questions, anything like that? Just to let you know, with the slide, the notes, I go on a little bit and talk about lab standards for calibration. You can spend some money there. There's a few things you can look at, and yeah, there's another presentation from K6JEY on how to set up a microwave station. So typically you need to use, you use surplus HP gear or equivalent to do that. And there's some good deals. And he talks about how to buy that stuff, what to look for. So there's the second presentation that's, on the server. So take a look at that if you're interested in microwave, and that'll give you some ideas. And so anyway, my thanks to K6JEY, Doug Millar, for that, and for his other suggestions and information, and also to my friend N6MN, who's been a longtime microwave guy, worked with him for years. And there's a picture of his test bench with some interesting things a little further in this package. So, and that pretty much covers it.
Okay, does anybody have any questions before we go? I'm going to have John go ahead and is going to kind of pan around here for kind of the group. And it's not really wireless, but it's kind of a work in progress. We spent some time doing it, and I know I've had a good time and learned quite a bit. So any suggestions that you have, please let us know. Or if you've got any questions before we end the recording, and definitely want to thank everybody for their time and hanging out with us on a Saturday morning. Wish we could do some more of this in person, but I'm hoping that you found this useful. Thanks again.
This is Curtis, KA0VBA. I remember an old instrument called a HP410B. It was used for measuring RF voltage on a coax without disturbing the coax. And it had a special probe holder that went in, I guess it had end connectors on it, and it went into the coax, and then this vacuum tube device went in the probe holder, and I assume it was capacitively coupled. Is there a successor for that thing that maybe uses solid state technology?
Yeah, I know what you're talking about. Yeah, I've seen that. And it's essentially an RF voltmeter that is optimized to work at higher frequencies. I've used what they call a vector voltmeter, similar kind of thing, but that's been replaced pretty much with the vector network analyzers. You know, as far as a straight RF voltmeter, you probably could do those measurements with a vector network analyzer, but you'd have to make sure that you have the right attenuators in place to do that.
The thing that made that thing unique was the ability to couple to a coax without disturbing the coax.
Oh, well, I mean, there are inductive probes, you know, for AC and DC power, but I've not seen anything like that because coax typically is so well shielded that, you know, you might pick up a little bit of leakage and you might be able to look at the frequency, but you wouldn't be making a voltage or a power measurement with any kind of accuracy unless you can get on the conductors themselves.
Right.
I've heard that 410.
You could use a coax T, but that still disturbs the coax.
Yeah.
Use an inductive T, one of the ones that has the sliding pickup.
Thing?
It has a sliding pickup that's adjustable, and you can actually calibrate that and figure out what your coupling is. It won't actually get into the line. It's just it's a pickup to couple it off the line.
Never used one of those before. Yeah.
Yeah, we use them all the time for tuning duplexers and checking for receiver sensitivity. They work very well.
That doesn't actually measure voltage on the line.
Yeah, you can't measure voltage directly with it, and you can measure signal level.
Yeah, because if you could measure voltage, you can calculate the voltage standing wave ratio, but you need, well, you know, actually the VSWR meters, they sample that way inductively. They typically, they're a pair of toroids, a piece of coax, a section of coax with connectors on it, and then toroids with windings on them, you know, wound oppositely. So you're getting power going one way and the other way. And then you're looking at those voltages. So that, you know, that's interesting.
I'm sure somebody makes it. I just don't know what the model is.
Yeah.
Is Doug Sharp on here? K2AD.
That makes sense. Yeah, I bet.
He's on. The question is if he's paying attention.
He probably went to the bathroom.
Yeah, some kind of an SWR meter would have a similar effect. But you know, they measure a voltage, but it would have to be proportional to get it calibrated to actually measure an accurate voltage like that. You could do it, I'm sure. I'd have to look. Yep. We don't find the vector voltmeters anymore, which is the 2-port version of that we use for tuning certain kinds of filters in the old days and working with synchronous detectors. But anymore, we just digitize everything, and that's all we look at the bits.
Willem, do you have anything to add before we shut it down?
Sorry, I was looking for my mouse to unmute. No, I just thank you again to Dean for running the presentation. Very much enjoyed that, and to the AV crew that ran all of the cameras. Appreciate you guys all being there and setting things up. So we hope to see you here for the next presentation, which is on the 29th. Chris Keller talking about the TMD 710. And then our next RMHAM University is on January the 6th when James Isaac is going to talk about batteries. But based on the questions we had today here, I think we have several tech talks coming up on all kinds of interesting topics like how do you use an antenna analyzer and things like that. So hopefully we will have some volunteers. Otherwise, I will have to volunteer a few people. So thank you, everybody. And hope you all have a happy Hanukkah, Merry Christmas, or whatever winter celebration you celebrate.